You may start. Okay, thank you.
So, well, thank you very much for the invitation, for having me. And yeah, sorry again for the little connection issues. I'm going to be telling you about some work I've done over the last few years with a main collaborator, Steve Shu in the US, but with significant input from collaborators in Bologna, so Roberto Casadio, Volker Kuipers, who was a PhD student of mine, who's now a Humboldt Fellow in Munich. And this guy is spectacular. If you have a faculty job, I think he's getting ripe for these kind of jobs, and I would keep a serious eye on it. And my most recent PhD student was Marco Sebastianuti, who promises to be just as strong. So I'm very lucky to be surrounded by a team of very strong young people. Oh, here we go. So in case I can't get through or you have to leave because of the delay, I'm going to give you the take-home message. So we have identified quantum gravitational corrections to the external metric of compact objects, or like stars or black holes, which contain information about the interior metric. And that's what we call the quantum hair. So it's a new form of a quantum hair. So we've shown that these results apply to black holes. Now, we've used this new feature of quantum gravity to discuss a new solution to the information paradox. We have methods that are UV independent that enable us to do calculations in quantum gravity. And we've applied these methods to revisit Hawking's original calculation and shown how quantum gravity modifies Hawking's amplitude. And we can also show that the black hole spectrum differs from that of a black body, and there's thus information in the radiation. So here's the outline. I'm going to very briefly tell you a little bit about the methods we've used to do these calculations in quantum gravity, so using effective field theory. And I'm going to discuss one example of one application, namely to stars, and I'll extrapolate to black holes. Now, this is in the framework of perturbative quantum gravity. If you like it, that's great, but it's not really necessary as such for the solution we have to the information paradox. This was really the way we got our intuition and motivation. So based on these ideas, I'm going to define the quantum states of the graviton field, which is really a non-perturbative statement. Then we'll go to the black hole radiation and its evolution. And then at the end, I will show you how we could, going back to the EFT methods, how we can use that to revisit Hawking's calculation. And I'll come to the conclusions. So the tool we're using is the unique effective action. And that's something that goes back to the 80s. So we had to refine some of it, but basically the idea is that you start from Einstein theory of quantum gravity. So there's nothing speculative. You're assuming that this is the right low energy limit of your UV complete theory. You integrate out the gravitons, so the massless degrees of freedom. And what you obtain is essentially a classical effective action where all the fluctuations of the gravitons have been integrated out. So you recover, obviously, your Hilbert-Einstein term. You will have potentially coupling to scalars. That could be interesting because psi would be a dimensionless parameter. I don't have anything new to say about the cosmological constant. It's just a normalized parameter in this framework. And then there are terms that we call local. So C1R squared, C2R mu, R mu, and so on. And terms that I'm going to call non-local, and that's a bit of an unfortunate term, but that's the one that people have used in the literature. There's nothing fancy here. It's simply because you integrate massless degrees of freedom out, you get log box appearing. So you get terms like R log box, R mu summary normalization scale. You get the same thing for the Ricci tensor, all the Riemann tensor terms. And you can actually massage this term back into these two using something that resembles the Gauss-Bonnet identity, which is a validating a curvature expansion. So this is really a classical field theory. You have to think of it as a classical field theory. I haven't solved quantum gravity because the theory is still non-normalizable, but there are some things that we won't doing that. So you have to think of this action as a curvature expansion. And if you think of our, where to apply it or where we could apply to in a universe, well, unless you get really close to singularity, whether it's the Big Bang one or the black hole singularity. The curvature is fairly weak everywhere. So, and unless you are doing physics out the curvature itself, or within, if you look at quantum black holes that have masses 10 times, up to 10 times the Planck mass, you can apply these ideas and they work very well. So what is the benefit of this action? Well, the good thing about it is that these non-local operators have Wilson coefficients that are calculable from first principles. And if you have an observable that only depends on that part of the action, and I will show you cases where that is applied, where this applies, you have UV, or you have predictions of quantum gravity that do not depend on the UV completion of your theory. So the coefficient B1, B2, B3 depend on the particles that you have integrated out. And for the graviton, those are these numbers. And these numbers for the graviton are specific to the unique effective action. Loosely speaking, the issue is that when you calculate an effective action, you have to be careful to keep gauge invariance for your Wilson coefficients. And that's something that's very well understood, for example, with high temperature QFT, but the same applies in gravity case. So there's a way to define your effective action that ensures the gauge invariance of the Wilson coefficient, and that goes back to the work of Barvinsky and Wilkowinsky. So Wilkowinsky especially started this. He was the advisor of Barvinsky in the early 80s. So that's something that people have understood. The knowledge got lost a little, and we had to refine a few things. But that's basically the benefit. Now, the price to pay is that we do not know the C1, C2. So from our point of view and so on, there's an infinite number of parameters of the local action that we don't know, unless we match the effective action to a UV complete theory, like string theory. And then in that case, C1, C2, and so on are given in terms of the way you compactify your extra dimensions. So we're going to just treat them as 3 parameters and that's a price to pay. But we can have predictability if we have an observable that depends only on the non-local part of the action. So the log box, I want to take the Phys.Rev.Lett beast. It's nothing but a distribution. I mean, basically, you can think of it as a Fourier transform of the log minus p squared that we typically get in Feynman diagrams. Now, we're working to second order in curvature in most of what I'm going to tell you about today. And in that case, it's sufficient to look at the distribution flat space-time. And that's an object, so that you basically have to deal with an object like that looks like this. And technically speaking, the calculations are not very complicated. What you're going to end up doing is folding that distribution with curvature scalars, tensors, and so on, and getting your field equations that way. So I will show you an example. So that's the one that gave us this intuition of quantum hair. So we're going to use this unique effective action and we vary it with respect to the metric. You recover Einstein's equations here, and you get a contribution from the local part of the action and a non-local part of the action. And these are calculable from your effective action. So the simplest model for a star you can think of, that's how we got started. You think of a homogeneous and stationary distribution of matter. It's isotropic. You pick a radius RS and constant density inside and 0 outside. So if you want to apply this method and do analytical calculations, you'd better make sure that you have a model that has classical solutions in GR that are known and that are analytical. So in that case, the model is simple enough that in GR, you know that inside you have the interior Schwarzschild metric. The mass is given by the Misner-Sharp mass. And outside, because of Birkhoff theorem, you have the Schwarzschild solution. So what we do, you take your effective action, or the field equations you obtain from your effective action, you do perturbation theory around your classical solution, G mu nu, and you're looking for the quantum correction that is due to the extra bits in your field equations. And so after some fairly simple algebra in the end of the day, you obtain a correction to the classical value outside the star. And so we rewrote the result of the Planck length. So those are very tiny effects. But if we look at the r to the -5 terms, so you have r squared here, r squared here, so that's r to the -5. we find a quantum correction to the metric that is proportional to g squared n m over rs to the cube. So rs is the radius of your star. So it is a quantum gravitational effect that is proportional to the density of the source object. The other thing to observe here is that you have a violation of Birkhoff theorem, which is really interesting. So if you go beyond GR, you will have a correction to the 1/r potential. Now, this is not quite enough to convince you that this would apply to a black hole. So we revisited this work recently, taking an Oppenheimer-Snyder model, so the collapse model. So things do get a little bit more tedious, technically speaking, because your distribution is now space and time dependent, but we can still do the calculation in a reliable way. It boils down to replacing Rs in these equations I was showing you here by Rs of t, loosely speaking. And the nice thing with that is that we now have a system which is time dependent, and we can think of the collapse, and we can follow the quantum correction I was just describing to you from a distant observer point of view at all times. And we can see that this correction survives to the time where the radius of the star, or of the dust bowl, if you want, reaches the Schwarzschild radius, and you can argue that you form a closed trap surface, or you use a Hooke conjecture to argue you form a black hole. So we have strong indications that these corrections to the R to the minus that goes as R to the minus 5, the correction to the metric survives through the gravitational collapse. And in principle, it is measurable by a distant observer. So a distant observer could differentiate between two black holes, and by measuring this, you could know what Mathur distribution form which black hole. So that's really this quantum hair. It's a new kind of hair on black holes. And I will show you at the end again that this hair affects or rather I will show you that this hair affects the evaporation that Hawking had discussed. Now, that was using EFT methods. If you like it, that's great. But if you don't, that's fine as well, because what I'm going to tell you now doesn't depend on it. And this was really a matter of getting some intuition, or whether that's how we got our intuition for what follows. So what I want to discuss now is the asymptotic quantum state of the graviton field. So I'm going to think of a compact source of matter that has an energy eigenstate with eigenvalue E. And I'm going to try to write down the graviton quantum state for that object, so psi g of E. And that's going to go in the same way as you would have for QED. So you think of the quantum state of the U1 vector field, so the Coulomb potential that is created by a charge. And you know that it's given by an object of this type. So if you have exponential, the charge Q, integral d3k, Q of k, B dagger K acting on 0. And B dagger is a linear combination of creation operators of the non-propagating modes of the photon. So basically, that depends on the gauge, but it will be the temporal and longitudinal modes. In the case of gravity, you're going to replace Q by the energy eigenvalue of the source state. And obviously, the coherent state modes are then the temporal and longitudinal modes of the graviton. So in both the gauge theory and the gravity case, the asymptotic state will be fixed by the Gauss law by a constraint quantization. Now, I don't have too much time to get into that discussion, but you could get similar result thinking about the double copy relations for those of you interested in amplitudes. I think there's a nice application there. And that's something we're looking at in more details as we're speaking. So let me now try to specify psi g of E. So it depends on the energy. So each energy eigenstate will be a distinct energy eigenstate of this compact source, has different graviton quantum states. And you will have a semi-classical matter configuration that you can think of as a superposition of energy eigenstates with support that is concentrated some fairly narrow band of energy. So you're going to have some uncertainty because of quantum mechanics, essentially. So you're going to have a band of energy, but it's going to be a narrow band of energies. And so you can write psi as the sum over n, Cn psi n. And psi n here are the energy eigenstates that have eigenvalue En. So we can write the gravity state as a superposition state. So psi g is the sum of n Cn psi g of En. Now, in QED, you have the intuition again from QED, the long wavelength photon will couple to the total charge of the composite object. In the case of gravity, the long wavelength gravitons couple to the energy eigenvalue of the compact object. So the semi-classical compact source produce external graviton states that are complex superposition given by this equation psi g. Now, the star that we looked at earlier were just a concrete example of this result that doesn't depend on the EFT methods. So that's a purely non-perturbative statement. Right. How can we use this to revisit the information paradox? So you all know that some 50 years ago, almost, Hawking has shown us that black holes, when you put quantum mechanics in the game, are very interesting. They become thermal objects, so there's a radiation, and they eventually would evaporate. And the question, what happens to the information that went to the black hole? So that's a very nice way to, or it was a very nice paper. It's a very nice result. But if you could phrase it as black hole cause pure states evolving to mixed states. But this is not so easy to track in terms of assumptions you're making. And the best formulation of the paradox goes back actually to Mathur. So we're talking 2009, 2010. There's a series of very beautiful papers that I strongly recommend you would look at. And the beauty about Mathur's approach is that you can actually track how the entropy grows. And he's very careful about which assumption is made and where. So he starts from the notion of a nice slice, and loosely speaking, a nice slice is a space-like surface that intersects both the interior of the black hole and the emitted Hawking radiation. So the good thing about this nice slice is that you can ignore strong gravity. Gravity is very well behaved there, and you can think of just using flat space-time, essentially. So let me review Mathur's formulation of the paradox. And I'm going to use, for those of you who know his papers, exactly his notation so that I don't confuse you by introducing new conventions. So I'm going to call, so you think of modes, so Hawking radiation, quanta being created on this slide. So there's going to call the first one B1. So that's outside the horizon. B2 will be the second one, B3 will be the third one, and so on. And inside the horizon, I'm going to call them E1, E2, and so on, and weather. That's what Mathur picked. So we start from this initial nice slice. And you're going to have the only matter state you have is the black hole, psi index m, and you have no radiation yet. So you have your black hole that sits there, that at some time t, you have the first emission. So you emit B1 going outside, E1 going inside, and you can write down the state for these modes in this schematic form. So you have 1 over square root of 2 to normalize it, and we use the occupation number of a particle mode. So 0 E1, 0 B1, 1 E1, 1 B1. Then these particles move away, and you form the second pairs form. So sorry, I should first tell you that the entropy, the integral entropy here goes as log 2, right? That's straightforward. So the outside, the state outside the horizon, so the B1 is entangled with the state inside the horizon. So that's the E1, and the entropy, integral entropy is log 2. So then these two move apart, and you're going to form your second pair. So you form B2, E2, they go apart. Then you form E3, B3, E3, they go apart. And every time you assume that they move apart sufficiently, so there's no influence on the previous emission. So after n steps, you're going to have your black hole. Then you have the first state I've described to you, the second one, and so on. So what you have here is an initial amount of state that appears in the tensor product with all the other quanta. And that's because all the pairs have moved further away every time they produce. So there's no connection to the matter state to leading order in the Hawking process. And now the problem is the following. If you calculate the entanglement entropy. So the modes BI are entangled with the modes EI, and the black hole with the entropy N times log 2. So for every emission, you get a log 2. For N of them, you get N log 2. So the problem is that at some point, your black hole will have evaporated completely. The BI, so the quanta outside, will be entangled, but there's nothing for them to be entangled with. And so you have a pure state, psi m, that has evolved in a mixed state that is described by a density matrix. Now, Mathur is a very careful and smart guy. He's going to tell you, well, okay, fine. What I've done is neglecting completely quantum gravity, and I acknowledge that there will be some corrections, and they'll be small, and I agree with that, so we call them epsilon. And these corrections to the Hawking evaporation cannot change the qualitative picture I've given you, because they only change the entropy by minus epsilon. So you get log 2 minus epsilon with H emitted quantum. Now, to prepare you for what's coming, this formulation makes a strong assumption, saying that you have a semi-classical space-time background. There's one Penrose diagram, basically. And it doesn't address the possibility, or consider rather the possibility, that the entanglement is between different background geometries or gravitational states. So what I'm going to argue is that the black hole, or the geometry as you wish, and the Hawking radiation form a macroscopic superposition. That's going to be one of the differences. So let me try to gather what I've told you together and see how we can go beyond Mathur's formulation. So we have two key results, I believe. So we have the asymptotic state of the asymptotic graviton state of an energy eigenstate source is fixed to leading order by the energy eigenvalues, and we can express it as a coherent state which depends on this value. Now here, there's an assumption that is a very moderate one, and namely that you have no accidental energy degeneracies, so that you can have a one-to-one map between the graviton states and the matter source states, and that's something that is not crazy. I mean, we have many examples of many particle system where you will not have such degeneracies unless you have a symmetry. So that's a folk theorem, basically, but a very reasonable one. So semi-classical matter source produces an integral graviton state. And the second finding we have is that the quantum gravitational fluctuations, so the loop of the gravitons, produce corrections to the long-range potential. For example, using these EFT methods, we found this R to the minus 5 term. And these coefficients, or the coefficient of this term rather, depend on the internal state of the source. So that is an explicit example of how the graviton quantum state, or in that case, the corresponding semi-classical potential, is able to encode information about the internal state of the black hole. Now, none of what I'm telling you now is sensitive to the UV complete theory of quantum gravity. I'm using purely low energy results. So let me now tell you about the way we see the evaporation of the black hole. So I'm going to put things a bit together. So I start now, and I'm going to establish our notation. I'm sorry, I have to burden you with our notation because that's the way we can talk about it the most efficiently. So we have the graviton quantum state, so the exterior geometry. So we have psi I is a sum n Cn psi g of En, and we rewrite this in terms of the geometry of the black hole, but the exterior one. So this, again, it's a semi-classical state, and there's a support that is concentrated in some range of energy E. And in that support, although that range, the Cn are the largest. So to make our life a little bit easier and not overburden the reader with notation, when we talk about Gn, we mean the geometry with all of the other quantum numbers, so just the of the black hole, so just to make our life a little bit easier and not to confuse the reader. When it comes to radiation, I'm going to call Ri. Those are all the quantum numbers of the emitted radiation particle. So that will be its energy, delta I, its momentum pi, the spin SI, the charge QI, any other thing you have. And I can basically specify the final n radiation state by giving you R1, R2, R3, and so on to Rn. So that's basically what defines the final state. Now, I'm going to call the amplitude for the emission of a quantum Ri from the exterior metric of the state psi g, alpha of E, comma Ri. So Ri are the quantum numbers of the radiation. E is the energy of the black hole. And so at leading order, this is just the calculation that Hawking did. Okay, so no surprise here. So let me mention a few things about the amplitude alpha. Again, if you do not like the EFT calculation, it's fine, because the argument I'm going to make, again, doesn't depend on that. Mathur and everybody believes that there will be corrections from quantum gravity to alpha. And people have long discussed the shape of the corrections you could have. So if you're optimistic, you will think they might be perturbative corrections, in which case they will go as S to the minus K, so S is the entropy. Or you could have exponential, so suppressed effects if they're non-perturbative, so exponential minus S. So these will generate additional dependence on E and Ri. Now, these terms will depend on the internal state of the black hole because of the quantum error we've discussed. Now, a while ago, these two papers have discussed this effect. And it's a counter-argument to Mathur's assumption that the epsilons don't matter. In the worst-case scenario, that is when the corrections are as tiny as possible in the case of the non-perturbative effects, they show that these small corrections are enough to purify a maximally mixed Hawking state. So when you calculate the density matrix, so the trace of rho squared, and you want to show that it's 1, you basically have a huge matrix that is sprinkled with very tiny entries, exponential to minus S. But the dimensionality of this matrix, of your Hilbert space, is going to grow with exponential of S, because you have a lot of states to sum over. And these tiny effects can be compensated by the size of your Hilbert space. So that was a counter-argument already to Mathur's argument a few years after his paper. That's why these guys would argue that the firewall already were not relevant. But this is something that is very clear. If you have a large Hilbert space, you can compensate tiny quantum corrections, so your epsilons may matter. So how do we see the the evolution of the black hole? So we start from the first radiation, so of the quantum R1. So we have our black hole, initial black hole. So I wrote the geometry here. And after the first emission, the black hole has lost a little bit of its energy. So it's going to be the geometry now depends on En minus delta 1. I've emitted the first radiation. So the state depends on this. The amplitude depends on En and R1, as I've argued. Then we have the second emission, exactly the same scenario as with Mathur. So we wait a bit, then we emit the second emission. We have the amplitude for the emission of the second particle. Now, because the energy had dropped a little with the first emission, alpha now depends on En minus delta 1 and R2, which is the quanta I've just emitted. And the state here now, the energy of the geometry has dropped a little bit by delta 2, and I have R2 appearing here. Now, I'm going to do this n times, and after n times, my black hole is essentially gone. Now, I'm going to rewrite this line for you on the next slide just to make things a little bit easier so we can discuss it. So the black hole is gone, so I omit the geometry here. I have my final radiation state. I've got R1, R2 to Rn, and I have these amplitudes for the first emission, second emission, third emission, and so on. So when the black hole is no longer gone, it does no longer exist, there's no horizon, and space-time is essentially flat. And the final radiation state is a complex superposition that depends linearly on the initial black hole states. And so under time reversal, the radiation state evolves back to the original black hole quantum state. So this is manifestly unitary. So the quantum hair allows, again, as I've argued, the internal state of the black hole to be reflected in the coefficient Cn, and it will thus affect the Hawking radiation. And again, I stress that these expressions are manifestly unitary, and the final state is manifestly a pure state. So for each initial state that is given by Cn, there's a final state, a final radiation state. And on the time reverse evolution of the final radiation state, you obtain the specific initial state. Now, I will discuss that a little bit more in a slide or two, but the final radiation state is a macroscopic superposition state. So I will argue that the black hole has moved macroscopically. So not only are you summing over quantum geometries, but you're summing over macroscopic geometries as well. The quantum hair also explains or gives the mechanism by which the amplitudes can depend on the initial state. So basically what we're providing here, I think, is for the first time a physical picture of how information is encoded in Hawking radiation. Now, why do we have this unitary evolution? What is different here? So if you want to show that there is a problem with unitarity, like Mathur was doing, you need to show that you can factorize your state like this as a tensor product. We can't, because each of these amplitudes depend on the previous step. So factorization is assumed in every formulation of the information paradox, but I've shown you that it's not a valid assumption. It doesn't hold, actually, when you do things correctly. So here we see that it's violated because of the external graviton state depends on the internal black hole state. So let me emphasize really the macroscopic superposition, because that's really something very interesting. So we have a distinct radiation pattern, so R1, R2 to Rn, that correspond to different recoils of the trajectory. So think of it this way. You have your black hole that is sitting here, and it's going to start to emit a quanta in one direction. So there will be a recoil. It's tiny, yes, because it's just one little particle. But there will be another recoil in that direction. And after n step, your black hole will have moved quite a bit macroscopically. So that's something that is quite well known, or maybe got lost a bit in translation, but it goes back to an argument by Page in the early 80s. So in the end of the day, your black hole, that's what you show in these pictures here, your black hole would have moved macroscopically. And you have to sum over all these geometries. So basically, Mathur and other people discussing the paradox, saying there's a paradox, assume that your Penrose diagram is not changing, and that they're trying to solve the paradox on one given ice slice, but this is not the way it works. Your Penrose diagram is going to change with time because your black hole moves, its quantum numbers are changing, and so on. And you have to sum over all these space-time geometries. And some of these geometries, well, there will be quantum geometries as well, obviously, but there are also macroscopic effects, hence the macroscopic superposition states. So we now come to the question of how would we modify, or how would we revisit Hawking's original calculation. So you have to decide how you model your black hole when you're discussing quantum gravitational correction to the black hole. So you may know that people like Duff or Donahue have been working on that topic for a long time ago, and they were looking at a situation where they have a delta function of point mass. So first of all, you know that in GR, you cannot have delta functions, or things are more complicated, let's put it that way. Secondly, it's not empty space-time. So I think the right way to think of it is really to take Schwarzschild as your solution and look at quantum correction to that. And so that's also what Hawking did. So he assumed Schwarzschild as a geometry for his calculation. Obviously, this is not quite relevant to astrophysical black holes, because you know that a black hole is not an empty space-time, a real black hole. But let's nevertheless take Schwarzschild. So in that case, there's no second order correction. So it's second order in curvature, there's no correction. And we have to go to third order in a curvature. Now, here we have a dependence on the local part of the action. There, it's easy to have the non-local part as well. I won't bother you with this because I just want to illustrate what's happening. We're talking about very tiny effects, but again, they will be interesting. So that's the correction to the metric, to the Schwarzschild metric we're getting. So what we did was basically to reproduce, to extend rather Hawking's calculation. So we go in the background of this new metric, and we look at the emission of pairs of scalars. And we have redone exactly the calculation that he did, basically the Bogoliubov transformation. And we can show that the amplitudes alpha and beta now depend on the correction to the metric. So the quantum hair, so the deviation from the 1/r potential, induces a quantum correction to the amplitude for the production of the radiation. And again, that's the mechanism by which information would escape from the black hole. Now, Hawking's calculation has one limitation that, again, has been well understood for a long time. It did not take energy conservation into account, so the black hole remains the same mass. And if you want to take energy conservation into account, there's a well-known trick that goes back to Perrick and Wilczek. And they were able to map the problem to a tunneling issue. So we, again, extended their work. We look at a particle in the curved background. And basically what you need to do is to calculate the imaginary part of the action because you want to know the tunneling rate. So the interesting part here for you to consider is we recover the correction from the metric coming here. And here is the term that Perrick and Wilczek obtain. That's the deviation from, well, basically the energy shrinks because of the emission of the, well, rather the 2m shrinks because of the emission of the quanta with energy E. So when you look at the tunneling rate for the, and its quantum correction, that's the result of Perrick and Wilczek coming from energy conservation. And that's a correction from quantum gravity. So with that, you can calculate the spectrum that follows from this tunneling rate. And we see that there's this dependence of omega that Perrick and Wilczek had identified, and we get this extra term. So for small omega, we get the Planck distribution with the modified Hawking temperature here. And basically that shows that there's information about the interior state of the black hole again in the radiation of the black hole. So the Hawking amplitude depends on the quantum corrections to the metric, the quantum hair, but the power spectrum also depends on these corrections, and it does not match that of a black body if you assume energy, or if you implement energy conservation. So again, that's not our work, it's Perrick and Wilczek. But we see that it's even more relevant once you include the quantum gravitational correction. So in a sense, it's a way to understand how the alphas in the unitary evolution I was showing you could be calculable within QFT methods. So let me come almost to a conclusion. I would like to make a bit of advertisement for this unique effective action and give you an idea of how powerful it is. So over the last 5-6 years, we've been able to show that in quantum gravity, many of the theorems that you have in GR do not hold. So Birkhoff doesn't hold. I've talked about that today. One thing I haven't mentioned is that singularities theorem will not hold as well. No hair doesn't hold. Now, the validation of Birkhoff theorem and the no hair are the tools that we use to discuss information paradox. But it would really be interesting to keep working in this direction to see whether there are more surprises to come. Basically, because of the theorems that you have in GR that tell you that something can happen, that are classic, basically phenomena that are classically forbidden, you may find that they are actually allowed at the quantum level. And that might be a way to potentially probe quantum gravity by finding some some phenomena that can't take place classically, but that happens at a quantum level. And an example of this that has been well discussed in the literature is entanglement due to gravity, and that's a motivation for people to think about macroscopic superposition system and hoping that they could be entangled through gravity to prove that gravity is a quantum force, really. So let me come to the conclusion now. So we have very well-established methods that allow us to do calculations in quantum gravity in a model-independent way. Now, maybe in a bit of a provocative way, I would argue that in our universe, this might be all we need, because even inflation is taking place at scales below the Planck scale. And we should be able to do calculations for any relevant phenomena in our universe using these methods. If we're lucky, we can have a situation where the observable only depends on a part of the action that is calculable and model independent. So you could have actual model independent predictions of quantum gravity that should apply to any UV Calmet theory that has GR as the low energy limit. So I've shown you that the quantum gravitational corrections to the metric of stars and black holes contain information from outside, from inside these objects. And that's what we call a quantum hair. So it's a new type of hair. And I've presented generic expression for the quantum state of the graviton field that doesn't depend on these EFT methods if you don't like them. And then I've used these results to reconsider the information paradox, the black hole radiation and evolution, showing that it is a unitary process. And finally, I've shown you, going back to EFT methods, how to use these techniques to revisit Hawking's calculation and to calculate quantum gravitational corrections to its amplitude in the spectrum. And again, we find a deviation from the black body spectrum. Thanks a lot for your attention.
Thanks a lot, Xavier, for this very nice presentation. It's been certainly very interesting. I don't know if there are questions in the audience.
I'm sorry, I've been a bit fast, I know, but I was trying to make sure that I would stay within your...
Okay, perfect.
The reason for...
Yeah, I have actually... Yeah, sorry. I have actually one question, Xavier. So if I've understood correctly, I'm not an expert in the field. So you assume that outside the black hole, there is the emptiness, no? I mean, there is only the radiation that you generate through Hawking, through the Hawking process. Okay, but shouldn't we take into account the back reaction of radiation outside the black hole? So
well, this is essentially what happens when you're saying that your black hole is going to move.
Okay.
And so there will be a small kick back on the geometry. And you're perfectly right. That's one thing that people ignore completely. Mm-hmm. And again, I'm arguing that all these things depend on the previous emission. So my alphas depend on what has happened before. And again, that's another issue with what people have done before. They're assuming things are factorizable, but they're not. Okay. So I completely agree with what you're saying. And that's a very important point. Thank you for asking this question.
Thanks, Xavier. I think Joan has a question. Sorry, Joan, we cannot hear you. You have to unmute.
I don't know if it's me, but I don't have sound at the moment.
Can you hear me now?
Yes.
Yes, perfect.
Please.
Now?
Yes.
Okay, good. Okay, so thank you for your nice talk, Xavier. I have just a question concerning the pressure of radiation in the evaporation of black hole. I understand that there is also a contribution here, right?
Yes. So exactly.
And I want to understand whether, I mean, if there is an equation of a state associated to this pressure.
Yeah. So this is something I haven't spoken about today, but we have reconsidered the thermodynamics of black holes. And looking at quantum gravitational corrections. And one other thing we can show is that at to second order in curvature, we do get a correction to the equation of state. And that correction looks like a pressure term.
Yes, but I would like to understand if this pressure is something that I think that there were already calculations on this, right? So what is new in this result that you provided here, which depends on
Okay, so what
the type of particle, the spins, and so on and so forth?
Okay, so the part that is new is that we are saying that these amplitude depend on R1, on the energy of the system, and you basically have this sum. So the second one would depend on En, delta 1, R2, and so on. And you have to sum of all these terms, and these terms will not factorize. So in terms of the information paradox, that's really the new feature. The fact that you cannot write this test as a tensor product. Once you've shown that, you've won, basically. So I'm not sure I understand your question correctly, but if so basically it's not of this type. That's incorrect.
Yeah, but I mean, as a macroscopic result, do you have? Can you provide some form of equation of a state?
So again, so if you're asking what is the entropy of the black hole, that I haven't spoken about that today. So in terms of the thermodynamics of the black hole, we can revisit. So basically what you do, you know about Wald formulation for when you calculate the entropy of the black hole. So it's straightforward to extend to apply to our case. And we find that the thermodynamics changes and you have a term in the equation of states that looks like a pressure term. That is something that was unknown. But that's another thing that I haven't talked about today.
Yeah. No, but I was interested in this to understand the result.
Well, I'll send you the link to the paper if you want. I'm happy to chat with you more about this if you would like. But it's basically so you have a quantum correction that is not a contribution to the temperature. So you find the temperature like Hawking did, and Wittgenstein-Hawking. But on top of that, you have a new term in the equation of a state that looks like a pressure. So that's quite interesting because that means at the quantum level, you don't just have a temperature, but you have a pressure as well. We're talking about Schwarzschild black holes there.
Yeah.
I'm not talking about it. I mean, it was known you could have. So if you put a cosmological constant, you have things that look like a pressure term, but we don't do that. We start from Schwarzschild, and we get at the quantum level this pressure term. So I couldn't cover all the work we've done in the last 5 or 6 years on that topic, but there are some quite interesting results. And if you're like this kind of physics, we have the tools to do the calculations nowadays in ways which I believe is reliable.
I have another question, if you allow me, just a short one. I mean, this is connected with this Birkhoff theorem that, I mean, the deviation from Birkhoff theorem is the third order effect, right?
Well, it's at second order in curvature, which, it's not so surprising because Birkhoff theorem goes back to the fact that you have second order differential equations. When you start to have fourth order terms, like we have at the quantum gravitational level, there's no reason to believe it will hold anymore. So those are tiny effects. I'm not disputing this, but that's where things could be interesting. If you have a system or if you have a phenomenon that is not allowed in GR because of a theorem like this, but this theorem is violated at the quantum gravitational level, you may have small effects that would be the dominant one. There would not be any background. So think of an object like a pulsating star Birkhoff tells you there's nothing outside because it's spherically symmetrical, I will get a correction to that star. That would be an example where you could have a deviation from that would be leading order. So I think that would be one direction worth thinking about. If you take the list of things that you know are forbidden in GR and see what happens at the quantum gravitational level, see whether you can find an effect that would be interesting. I see there's a raised hand. Sorry.
Yes, Jordi, please.
Did I answer your question?
Hi. Yes, I'm Jordi. So, yes, thank you for your talk. So, I'm not really into this field very much, but I wanted to ask one thing I'm curious about. You mentioned also about that these quantum gravitational perturbations also have information about the internal structure of a star, right? So even a star which is, not collapsed, right? Not a black hole.
Yeah.
Okay, but then this is a bit puzzling to me because I thought, this quanta from gravitational field will only have quanta of a wavelength comparable to the radial scale of the gravitational field, right? If you take the Earth, it's like the radius of the Earth, the smallest wavelength you have. So, whereas of course the contents of such a thing have a huge number of degrees of freedom, right? So, can you count? Is there any counting of internal states, internal degrees of freedom, the usual problem, right, with black holes?
You're asking me something very difficult to answer in a sense. Well, let me explain why. The example I've shown you is a trivial star where you have a constant density.
Yes.
And then you see that there's only one parameter in that case, it's density.
Yes.
So that's where we find this deviation. Now, what we have done in the same paper is look at stars that are made of different layers.
Mm-hmm.
They have the same mass overall, the same size, but they have layers with different densities. And we can show that, I don't have the slide with this result because I was trying to minimize the amount of time I spent on this, but we can show that the two-layer star would differ from the one ball star, and that you can in principle measure the coefficient of the two different terms and identify the two different densities. And actually, there's a paper that came out a few days ago by another group extending our work, doing that for n layers, and they get the same effect. They see that you have this external correction that depends on the n layers.
Yeah.
Okay. So now, to come back to your question, the problem is that if it's more complicated if you ask me to do a full quantum mechanical analysis of the situation here. I have a classical source.
Yes.
But our equations, if we were able to solve them for the problem you have in mind, I'm almost certain would give us, well, I know would give us the same answer. You would have corrections to whatever classical solution you have that depend on the complicated T mu that you're trying to describe to me.
Okay. But I mean, in the case of black holes, right, you have an entropy that goes like the area. So,
well, in the case of black holes, but it's not an issue, right? I mean, it's simply so if you take, for example, the Oppenheimer-Snyder model, which is one of the only models we have that is solvable classically of a collapse model, you can show that the correction that I'm describing here appears again. Now things are a little bit more complicated because it depends on RS of t over RS at 0. So there are some slight modifications, but they look very much the same. And you can show that these corrections survive throughout the collapse. So that's this paper.
You cannot count the number of degrees of freedom. So, because the surprising thing is that the number of quanta that the black holes is going to emit is very large, of course. So
right. Okay. But that's yes. Thank you. But that's, if you want this kind of discussion, I would tell you, forget the EFT. Okay. Use the quantum state argument, the non-perturbative argument I've given you.
Okay.
And indeed, my whole point is what I was making here. Let me find it, please. Here. Actually, it goes back to these two papers.
Yeah.
Even though you may have a very tiny correction, let's think of a non-perturbative correction just for the sake of it.
Yeah.
That's the worst case scenario. It would go as e to the minus s, where the entropy, s is the entropy of the black hole.
Mm.
So that's minuscule. But you're right, because the Hilbert space is so big, the matrix you have to sum over is huge, and it will go as e to the s, as you were saying. And that will compensate the smallness of the correction. So those are very beautiful papers making this point. And that's not something we can see with the EFT. So that's why I was telling you the EFT is there to give us the intuition. But the real argument is actually non-perturbative. It doesn't depend on any of the details of the EFT. The EFT was just there to make us realize that we could impact the outside metric from the inside. The quantum hair, basically. But that's exactly the point you were making, which is a very good point. Thank you for your question.
Yeah.
Did I answer it in a satisfactory manner?
Yes, thank you. Yes.
Xavier, this metric that you were showing before with this r to the minus 5 correction.
Yes.
So this is due to the modified gravity terms, no, in the action.
That's right. Yeah.
Okay, but once you fill the space with radiation, shouldn't the metric change?
Yeah. So
because you have a departure from empty.
Yeah, you're completely right. And again, I haven't emphasized that enough. So what we're looking at with the EFT, what we can solve analytically, is a very straightforward model where you have a classical solution that is known in GR. The point you're making is exactly what I'm telling you here when I argue that the previous emission affects the new metric and so on and so on. And this point is absolutely crucial. And that's what people were missing in the resolution. They assume the black hole remains the same. It stays static where it sits, and that's not right. It will move macroscopically. Its quantum numbers, energies, everything will change. And the radiation, the same applies to the radiation. So that's described by these expressions here. You're entirely right.
Okay, thanks. Joachim?
Yeah, sorry, I'm confused because here the information that you have is the information about the black hole and the Hawking quanta that you have emitted, but I don't see here the information of what went into the black hole to form it.
Okay, so you have the alphas will depend on the geometry outside. And I've argued that the quantum state of the graviton, and I've argued both perturbatively as an example and non-perturbatively that the graviton quantum state has information about what's inside. So that's when I define this object here, I'm explaining that I have basically a superposition state that depends on the psi GEN. So those are all the internal states, if you want. Sorry, I can't hear you anymore. Are you happy with my answer?
Yeah, thank you.
Yeah, thanks. No, you're asking all the right questions. So you could have done this work yourself because these are exactly the questions to ask. And these are exactly the things that people have ignored for so many years.
Okay, I don't know if there are more questions. It doesn't seem so. Okay, Xavier, thanks a lot for again for this very nice presentation. It's been a pleasure to have you with us. and see you soon.
Thank you very much. Thanks again for having me.
Thank you.
Bye bye.
Bye-bye.
Bye bye. Many